Hi everyone, we are Table 7 and our project is the Water Wheel Energy Harvester. I'm Peter and with me is Austin. We also worked with Gunnar, Grant, and Jaden. We were requested to create a device that could harvest energy from an unused source in a unique way and use that energy to solve a problem that made the lives of the students and staff at PFT easier.
Using the project goals and requirements, we built a list of functions and constraints to begin our thought process and drive the direction of our brainstorming. Important functions include being able to harvest and measure mechanical energy and using that energy to solve a problem. Constraints include not interfering with the user's natural actions and creating a unique and cost-effective design. Once we assessed our functions and constraints, the first step we took was finding environments and situations where unused energy was being created by natural flow of action. Some of the situations we identified were energy created from foot traffic, vibration from the vending machine dispensing, water flow from the sink in the bathroom, and chairs rotating in classrooms. Once we brainstormed ideas to harvest wasted energy, we then turned to the next project requirement of putting that energy to use. To do this successfully, we would need to find a problem in the environment where the energy was being harvested that needed to be solved. In this process, the challenge we faced was finding a consistent problem that needed solving versus our harvested energy to create an addition that would novelly improve an experience. After deliberation, we landed on the issue of paper towel dispensing and how typically one paper towel is not enough to adequately dry your hands. Our solution to improve this problem was to create a device that would use our harvested energy to dispense 2 paper towels during the hand washing process to save the time the user would take to dispense 2 separate paper towels, while also effectively drying the user's hands. Now that we had our problem and solution, we created a customer profile that identifies to who and why a product that solves our problem would be appealing. Our answer for why our product would be of use is the time it saves over an extended period of use, and who this product would be for includes any user of the bathroom and paper towel dispenser manufacturers. By answering these questions, we can ensure that our product will have viable use by applying it to a marketable audience. With an established problem solution and customer, now came time to brainstorm concept ideas for a device that fit our parameters. Our concept included using a stall door and a pulley system to pull an arm with an attached cover to set off a hand sensor paper towel dispenser twice. The issue following this concept was bathroom layout and connectivity of a pulley system to the paper towel dispenser. With no path from any stall to the dispenser, it would be much less viable to create a device that collects and transports the energy over that distance without interfering with the bathroom user's natural flow of action. Our second concept was to have a water wheel attached to the faucet. When the faucet was on, the wheel would turn a spindle connected to a gear system that would cohesively rotate over the distance to the dispenser and turn the arm to dispense the towels. The problem with this concept would be transporting the energy from the water wheel to the dispenser effectively without user interference. With the water wheel directly attached to the faucet, it would make it difficult. Our other 2 concepts were centered around converting energy into electric energy that would power a motor to then turn the arm that dispenses the towels. The third concept was very similar to the concept 2. A water wheel connected to the faucet turns a gear system that runs a small motor that moves the arm of the cover dispensing the paper towel. This concept runs into the same problem as concept 2, but would clean up the overall gear system, resulting in less moving parts. Finally, our fourth concept used piezoelectric sensors to harvest mechanical energy from the footsteps in the bathroom. That energy would be used to power a motor that turned the arm of the dispenser. The problem with this concept was collecting enough energy from the footsteps to turn the arm and the placement of the sensors. The placement of the sensors is relevant because it would have to directly correlate with the hand washing process to ensure that towels are dispensed when the user's hands are washed and not too long before or after. If it did not correlate this way, someone else's towels could be taken beforehand, or the device would simply not have any time if it was after. Now that we had the project goals and each of our concepts outlined, we used our list of functions and constraints to build a decision matrix around our 4 concepts. First, we gave each function and constraint a weight out of 5 for how important we deemed it to be to fulfilling the project requirements. Then we gave each concept a score from 1 through 10 for how well we believed it fit the specified function or constraint. 1 meaning it fulfills it completely, and 10 meaning it is unable to fulfill it at all. The score out of 10 was then multiplied by the weight, resulting in a final score. All 13 weighted scores were added up for each concept, resulting in a final total. The concept with the lowest total was considered the best concept. Concept 3 came out with a score of 162, making it initially our selected concept. Once we selected a concept, we built a house of quality. We created a list of engineering specifications allocated to customers and the user and manufacturer. We ranked our list of functions and constraints from 1 to 13 in most importance correlating to the weight we give them in the decision matrix, 13 being the most important and 1 the least. Then each specification was given a score out of 3 for how relevant it was for each function or constraint. Those scores were multiplied by the importance and added, and then each specification was given a percentage depending on its coverage of the overall points given out. We then took each function and specification and compared them to each customer and gave 1 if the function/specification was irrelevant to the user, or 2 if it was relevant. These percentages were then used to identify the most important specifications, and this included energy output, voltage range, autonomous operability, and measurement capability.
Converting from rotational to electrical energy, we found that a well-designed water wheel source experiences an energy loss of more than 40%, mainly due to friction, heat generation, and incomplete energy transfer. We can expect similar or even higher figures for our device, and that would make using a motor overall inefficient. Converting to electrical energy at all is also less practical because the environment where the device is placed involves water, which could damage the longevity of the device. Once this loss of energy problem was analyzed, our preferred concept needed to be reworked. The same base concept of the water wheel was kept, but shifted toward a pulley system similar to Concept 1 and a spindle system seen in Concept 3 to transport the energy. This concept also included multiple revisions, including the addition of a trough for water collection and another rotation mechanism. The first component we will look at is the trough. This component is meant to collect the water used to wash the user's hands and redirect it toward the water wheel without interfering with the natural process. To avoid contact with the user's hands, it is angled downward to the drain at 30 degrees. Supports and later a hook that fit into the overflow hole were added to hold it in place. Walls were added on the front and sides for water collection. To ensure that it is waterproof and would hold its function over time, it was made entirely out of plastic and sealed with hot glue. The trough directs water to the second component of the device, the water wheel. This is the energy harvesting part of the device, as the redirected water is meant to turn the wheel and pull the belt of the pulley. As the pulley rotates, a wheel connected to the next component spins, driving the motion of the device. The belt's elasticity creates tension on the two wheels, so they rotate in unison. To avoid interference, it is attached to the back of the sink via Velcro. It extends out using a dowel so it can reach the trough and rotates about a small ball bearing. The original design had the water wheel placed horizontally at the bottom of the sink, but this placement did not fit properly on the rounded bottom and did not effectively catch water enough to generate any spin. By switching the placement of the water wheel so it vertically attached to the back of the sink and adding the trough, it gave much more control over the water flow into the wheel. The vertical change also offered the benefit of subtracting a change in direction, which simplified the build further. This concept drawing shows the original then revised version of the water wheel. The upper component of the pulley is connected to the water wheel via an elastic belt. This component is made up of two sections. The first is a wooden dowel that rotates about a ball bearing that is fixed to the bathroom wall via a Velcro connection very similar to the water wheel. It extends out from the wall 16.5 centimeters so both wheels are rotating on the same plane. The second section is a spindle that is attached to the pulley via a ball bearing offset from the center by 2.5 centimeters. This bearing creates a new rotation point and radius of rotation. The spindle is made out of 0.9525 centimeter dowel rod that covers distance between the upper pulley and the next component. Due to the tension from the belt, the dowel rod was flexing towards the water wheel. To eliminate this, support needed to be added. However, the supports cannot impede the rotation of the system, so a low friction tube was made to slide onto the dowel, and then the supports would be attached to this tube. This can be seen in the concept drawing displayed. This limited deflection while still allowing free rotation. The supports made of wooden dowels that are reinforced with popsicle sticks, and the connection points are hot glued to the tube side and velcroed to the wall and bathroom counter. The spindle extends over and fits into a guide. This guide is meant to set the radius for the rotation of the arm at 2.5 centimeters and allows it to spin about that circumference in front of the dispenser to ensure there's no contact between the two bodies. This results in the cover setting off the sensor in a repeatable and consistent way. The guide is made from the same plastic spool as the pulley wheels with the same radius. The spool is lined with a plastic track to eliminate any friction between the dowel and the ridges inside the spool. The guide was then connected to the dispenser directly via Velcro. The guide works in tandem with the rotation mechanism of the arm. This mechanism is designed with two rotation points, one connected directly to the dispenser via Velcro, and the other offset from the rotation point by 2.5 centimeters to match the radius of the guide. The second rotation point is connected to the arm that extends backwards to the guide and forwards to the cover. These two rotation points are made of ball bearings that cause the arm to rotate along the same radius as the guide, while it stays flat along the same axis the entire rotation. This section of the arm is made of two wooden dowels hot glued together and reinforced with popsicle sticks. The extension between the two rotation points is made of popsicle sticks and hot glued at its connection points. The other end of the rotation mechanism's arm extends forward to the front of the dispenser. This extension corners 90 degrees out across the front of the dispenser and has a 3x3 cover at the end. This arm rotates along the same path as the rotation mechanism and the guide, but in front of the dispenser. At the low point of the rotation, the cover fully shades the dispenser, emulating a hand, and this activates it. The rotation is meant to be completed in 10 seconds and results in 2 paper towels being dispensed over 20 seconds, which is the amount of time the user should take to wash their hands recommended by the CDC. This portion of the arm is made out of plastic hanger and plastic plates to keep it lightweight and require little support. Now that we've covered all the components, here's our final bill of materials, and here we include all our parts and their corresponding cost, and our total cost came out to $38.69 per unit. While our device is made for hand sensor paper towel dispensers, most of the dispensers in PFT are turnstile dispensers. Because of this, our project proposes a hand sensor replacement dispenser of the same model as the other ones across LSU's campus. The reason for this replacement is because the force required to turn our device's arms is nearly 3 times less than the turnstile of the current dispensers at 8.545 newtons of force compared to 25.3 newtons respectively. To find this, a tangential force was applied to each device using 3 rubber bands, both at radius 2.5 centimeters. The length of the rubber bands was then measured at the instant where both devices turned over. We found our device stretched the rubber bands to a length of 12.5 centimeters and the turnstile 35 centimeters. We then used those lengths to measure the gravitational force it took to stretch the rubber bands to each one of those lengths by vertically attaching the mass to them. It took a mass of 871 grams to stretch the rubber bands to 12.5 centimeters and a mass of 2,579 grams to reach 35 centimeters. We can then find the power that needs to be generated for each device using these forces, circumference, and time to dispense. Our device is meant to cover a circumference of 15.71 centimeters twice over 20 seconds. So to dispense 2 paper towels, the equation for power would look like this, and find the output is 0.268 watts. Using the same circumference for the turnstile and the time to dispense 2 paper towels manually being 2.66 seconds, the equation will look like this, and find the power output required is 5.98 watts. This leads us to the conclusion that the hand sensor dispenser replacement is reasonable because a significantly smaller power output is required to automatically dispense 2 towels. To visualize our concept, we made a replacement in Fusion 360 with the arm portion of our device. The benefit of making this replacement and installing our device in PFT bathrooms is the time it saves per use. The average person takes 2.66 seconds to dispense 2 paper towels using the current dispensers. The average foot traffic of a bathroom in PFT is 42 entries per hour during peak hours. This was measured by tallying the bathroom entries over the hour of 12:30 to 1:30 p.m. on a Tuesday. PFT is open 16 hours during the week, so accounting for slower hours in the morning and night, we can safely bring our average down to 35 entries per hour. There's a total of 16 bathrooms PFT, so 35 entries per hour across 16 hours and 16 bathrooms results in a total of 8,960 uses per day. Multiplying that total number by the number of seconds each user would need to dispense 2 paper towels manually brings you a total of 23,833.6 seconds would be saved per day across all bathroom users. This is a collective of 6.62 hours saved per day. To show that our device could be implemented in PFT, we installed the device in one of the bathrooms, building off the current paper towel dispensers. The following video shows the device also does not interfere with hand washing process or the natural action of the user. Despite our design process and revisions throughout the build, the device failed to complete the task. After testing, failures were narrowed down to 2 specific points in the device. The first failure was the pressure of the water as it was delivered to the wheel. The pressure of the flow was not high enough to turn the wheel, as seen here. This next video shows that if the water was able to deliver enough force to turn the wheel, it would successfully turn the pulley and rotate the upper pulley and the spindle components as designed. To solve this problem, an improved design would increase the pressure of the water at the delivery by constricting the overall water flow through the trough component, as well as adding more blades to the water wheel so it would require less force to turn the wheel enough to reach the next blade. The second failure was when the spindle connected to the upper pulley that rotated about the guide had too much flexion, so the radius of the rotation shrunk over the distance to reach the guide component, causing the arm not to rotate. This video shows that when each end of the spindle rotated together as it was designed to, the arm rotates along the expected radius. We attempted to solve this problem by filling the empty space of the guide with a plastic disc that fit flush on the track but saw no change in results. In order to solve this problem, a stiffer material will need to be used for the spindle, such as a lightweight metal rod, to eliminate flexion. Despite our device failing to work, we left it installed in PFT bathrooms to test its longevity. Whether the device was successful or not holds little relevance to its ability to hold up over a week, because there are no parts that are intended to make contact with the user or any other body in the bathroom. We installed the device on Thursday, April 24th, and this picture displayed is from Tuesday, April 29th. Although 2 weekend days were included in the sample, the device proves it can hold up over multiple work days without maintenance.